We've spent a lot of time working in two-dimensional space, plotting points, graphing curves, functions, dealing with vectors. So now let's extend that into three-dimensional space, the space that we live in. What if I ask you to describe the graph of this? And you look at it, and you might want to pause for a second and not just listen to what I tell you it is, but think about it for a minute, and then go ahead and hit play and see if what you were thinking about matches. All right, when I look at this, I'm reminded of an equation in two dimensions that kind of looks like it. I remember looking at something like x minus h squared plus y minus k squared equals r squared. And yes, that was the equation of a circle which was centered at h comma k and had a radius of r. And so knowing that information, we can take that equation and easily graph it in two dimensions. So now when we extend it, what is that going to be? What is a circle in three dimensions? Well, it has become a sphere, so like a ball. And if I ask you what's the center of the sphere, I think that would be pretty easy to figure out. And you just take the opposite sign of the values, the constants that are inside the parentheses. So that'll be -1 in the x direction, +2 in the y direction, and +3 in the z direction. So that's your center. And then what's the radius? Well, the radius squared is 25, so the square root of 25, the positive root is 5. So it's a sphere centered at -1, 2, 3 with a radius of 5. All right, let's take a look at three-dimensional graphing. So we have an x-axis and a y-axis as before, but now we have a z-axis. And generally it's drawn from this perspective, with the positive x-axis coming out of the board, the positive y-axis going to the right horizontally, and then the positive z-axis is going up. And so you'll notice that, if I want to plot, and let me put positives on here. So this is the positive x, and that's the negative x. Here's your positive y, there's negative y, positive z, negative z there. So if I ask you to plot a point, for example, let's plot the point 3, 4, 7. So picture starting at the origin, which is now 0, 0, 0. And we want to go +3 in the x direction. So it would be out about that much. And then +4 in the y direction. And then +7 in the z direction. And we take our point somewhere up there. Now it's still hard to have the right perspective as to where that is. So you have to think about, in the coordinate plane, the x and y axis divided it into 4 sections, and we call those quadrants. Quad meaning 4. Well, now in 3 dimensions, we have 3 axes, and so that divides 3 space into 8 sections. And so we're going to call each of those sections octants. So we have 8 octants in 3 dimensions. And we number them just like we do in 2 dimensions. And so the numbering system starts off with the first octant, which from your perspective would be the one that's closest to you. So if you picture the XY plane, we have 4 octants above it and 4 below it. We're going to start with the ones above it, where z is positive, and that's going to define our top 4. So the first one is where x is positive, y is positive, and z is positive. So that's the one closest to you from this perspective. And then behind that to the right, where x is negative, y is positive, z is positive. And we're going counterclockwise, just like we do in 2 dimensions. So kind of opposite in the back on the top half, that's the third octant. X and y are both negative, z is positive. And then finally the fourth one is over on the left top half, and that's where x is positive, but the y is negative, and z is positive. And then we're going to continue right down underneath. So underneath the first octant is the 5th, and then to the right of that in the back is 6, and then straight back center is 7, and then around to the bottom left is 8. And so those are your octants. So which octant would the point 4, negative 5, 3 be in? Now you can try and look at the chart, but I don't think that that's as useful as to get the visual image for this. So if we picture we're going 4 in the x direction, negative 5 in the y direction, positive 3 in the z direction. So that's on the top half, and it's the last one as we're going counterclockwise around. So that's going to be in the 4th octant. All right, so hopefully that helps a little bit with perspective. Because now, let's start figuring out how we can do some things that we've done in 2 dimensions in 3 dimensions. So how would we find the distance between 2 points in 3 space? Let's say, for example, we have a point P and Q. And the P point has coordinates x sub 1, y sub 1, z sub 1, and Q is x sub 2, y sub 2, z sub 2. I want to find the distance. Well, we have a distance formula in 2 dimensions, which use the Pythagorean theorem. So let's extend this into 3 dimensions. So first, it would be helpful to think of the segment connecting P and Q as the diagonal of a cube, which connects the lower front left to the upper back right. So it's going right through the middle of this cube. Now let me add another point. And we'll call it R, so that I can make a nice right triangle here in green. Let me draw another green line here. There. Okay, now if you notice, R has the same x and y coordinates as Q, because it's directly below it. I'll draw an arrow so I can point to this. So notice this point here has the same x and the same y as this point up here. So I'm using the same labels here, x sub 2 and y sub 2 for those, but the z values will be different. But notice for here, the z value is going to be the same as for this point P, because they're both, the bottom of this box here is a plane that's parallel to the xy plane, and so the z values of those points will be the same. So it's important to understand the connection there. All right, so we're trying to find the distance from P to Q. Let me start with finding the distance from P to R. So for P to R, since that's in a 2-dimensional plane, the bottom of the box, and since they have the same z values, we can basically just think of a 2-dimensional plane which contains x sub 1, y sub 1, and x sub 2, y sub 2. And in 2 dimensions, we know how to get the distance between 2 points, and that's our distance formula based on the Pythagorean theorem. And so it's going to be, and you can write this either way, so I'm going to say x sub 1 minus x sub 2 squared plus y sub 1 minus y sub 2 squared. So that takes care of, notice now I'm looking at this green right triangle here. That takes care of this leg of that right triangle. Next, let me find the distance from Q to R. Well, for that, I've got enough room here. For R to Q, notice it's just the difference of your z values, because those are going straight up and down. This segment here is parallel to the z-axis. So to find the length of this, I just have to subtract my z numbers, because the x and the y numbers are the same. So it's just going to be z sub 2 minus z sub 1. And now that I'm thinking about it, well, let's leave it like that for now. Okay, so that's the length of our Q. Now, if I want to get my initial question was, what is the distance from P to Q? Well, that's the diagonal of this green right triangle. And I know the Pythagorean theorem tells me that this leg squared plus this leg squared equals PQ squared. So I'm going to use that idea. since I already have expressions for each of the legs. So PQ squared equals PR squared plus RQ squared. So if I take PQ will be the square root of PR squared plus RQ squared. And then if I substitute those back in, and in PR, I'm going to switch the order so everything's consistent. So PR squared, let me do another arrow here. When I square this, it basically cancels out the square root, and I'm left with these two quantities. Like I said, I think I'm going to switch the order of these subscripts, just so they're consistent with the z's. It doesn't matter because I'm squaring. So I'll say x2 minus x1, y2 minus y1. Okay. So PR squared is going to be x sub 2 minus x sub 1 quantity squared plus y sub 2 minus y sub 1 quantity squared. And then plus RQ squared, well here's RQ, z sub 2 minus z sub 1, and then I want to square that. So z sub 2 minus z sub 1 squared. And as you can see, it's probably no surprise that the distance from point P to Q in 3 space is this expression, which is really just an extension of the distance formula. We're just adding on an extra parentheses squared here, the difference of your z coordinates. So now that proves for us that the distance between 2 points in 3 space is exactly what you think it should be. How about finding the midpoint between 2 points in 3 space? You know, visually, if you think of, well, I have 2 points, if I make a segment between them, how do I find the middle of that? It seems way too complicated. But once again, let's just go back to 2 dimensions. How did we get the midpoint in 2 dimensions? We average the x and we average the y coordinates. So it's going to be the same idea here. I'm going to look at my x coordinates, 2 and negative 4. Let's average those. 2 plus negative 4 divided by 2. Then let's do the y coordinates. Negative 5 plus 1 divided by 2. And finally your z coordinates, 3 and 8. 3 plus 8 divided by 2. And so that's going to give me negative 1, negative 2, and 11 halves, or 5.5, however you want to write it. And so there's your midpoint between those 2 points. So in general, the midpoint formula, just like it is in 2 dimensions, you average the coordinates. There just happens to be one extra coordinate here in 3 dimensions. Okay, what else can we look at? What if I ask you to find the center and radius of a sphere? Now notice, this is not in the form that we had in the first example here. I need to have x plus or minus something squared, y plus or minus something squared, z plus or minus something squared, and then set that equal to a constant, which will be my radius squared. I need my equation to look like this, and I don't have that. So what I'm going to need to do, just like we did in 2 dimensions, you have to complete the square, like we did with a circle. We're going to do that with the sphere. So we're going to take the x terms, so we have x squared plus 4x, and we're going to want to complete the square on that. And then we have a y squared minus 2y. Complete the square on that one. And then finally we have a z squared plus 8z. We'll want to complete the square there. And then that plus 10, we're going to move to the other side, and it becomes a negative 10. All right, let's start with making the x as a perfect square. So we look at the 4 divided by 2 and square it. So we're going to need a plus 4 here. Because when I do that, I can factor it, and it becomes x plus 2 times x plus 2, which we can write as x plus 2 squared. That's the idea of completing the square. We want to make it a perfect square. So it's in that form like on the first page. But I added 4 to the left side of this equation. That's going to unbalance it, so I need to add 4 over to the right side as well. All right, let's complete the square for the y terms. We have y squared minus 2y, so we need to make this a plus 1. Remember how we do that. We take the coefficient of the variable to the first power, we divide it by 2, and we square it. And that's how I got the plus 1. All right, so when I do that, I can write this as y minus 1 times y minus 1, or y minus 1 quantity squared. All right, and finally, let's do it for the z. So let's see, let's back up. We added 1 to the left side of the equation, so let's add 1 to the right. All right, and lastly, go to a different color, go with black. Let's complete the square here. We're going to want to add 16. And so now that'll become z plus 4 times z plus 4, or z plus 4 squared. And I added 16 to the left, so I have to add 16 to the right. So now on the right side, I'm going to have 21 minus 10 is 11. Negative 6, 10, yes, 11. Okay, so now I have my sphere. Find the center. The center is going to be, we have a x plus 2, so the x coordinate is negative 2. Y minus 1, so the y coordinate is positive 1. And then for the z, we have a negative 4. So that's the center of the circle. And then what's the radius? Well, the radius squared is 11, so the radius will be the square root of 11. 3 point, whatever it is. And so that's how you find the center and radius. You have to complete the square. Now, one thing I want to mention, it's a little bit more work if, for example, we have a coefficient in front of one of these squared terms. So in that case, we're going to have to factor the 4 out first before we complete the square. And then that makes it a little more complicated for what we add on the other side. Let's try one more example. Find the intersection of this equation with the xy plane. So by now we know this is a sphere. And we know the center and the radius of the sphere. When I take that sphere, and if I take the xy plane, that's going to cut through the sphere, most likely, at some section of it. See if we can visualize this. So here's our sphere. And then if I want to slice this with a plane, we're going to wind up getting, it's hard to see here, but the intersection of the plane and the sphere is going to be a circle. And we know that the equation of a circle is going to look something like this. So it just depends on what the plane is that's cutting my circle. If it's the xy plane, that means z is equal to 0. Let's go back to what our three-dimensional graph looked like. Here was z, here's positive x, positive y, negative y, negative x, negative z. So the xy plane is kind of horizontal, straight in front of you, not going up or down. And that means that every point in the xy plane, what do you know about z? You know that z is equal to 0. So if z is equal to 0, we can take our equation and we can plug in 0 for z. So we're going to have x minus 2 squared plus y minus 3 squared plus 0 plus 6 squared equals 49. And so we get x minus 2 quantity squared plus y minus 3 quantity squared equals 13. And so that is the intersection of the sphere with the plane. It's a circle, and the equation of that circle is x minus 2 squared plus y minus 3 squared equals 13. Likewise, if I asked you, instead of doing the xy plane, if I said let maybe intersect with the xz plane, then what would you do? Well, the xz plane, that goes up and down in our picture here to the left, that means that the y value is going to equal 0. So you'll set y equal to 0 and simplify your equation. And likewise, if I said the yz plane, you would set x equal to 0.